Hey there, welcome back to Short Takes 331. Today we're going to talk about roots in 2D. And if you recall, recently we talked about roots in 1D. And so far that means we've discussed cases where we have a function of only one variable and we're looking for solutions to this equation f of x equal to 0 and without saying much about what the function looks like. Typically, the situation is going to be like this. We're going to have a function that we could plot on this xy plane. It depends on x only, and it crosses the x-axis at some point, and that's the root that we're looking for. But what if we were given a situation where we have a function of two variables, x and y, and we set that equal to 0, and we need to find the points where x and y satisfy this equation? So that will give us a whole family of solutions, which on the xy plane would look like this. So you have to think here that f itself is a function that you would plot on the z-axis, and then those are the values of f of x and y, and then x and y here will be the domain. And so we're asking for what points on that domain satisfy the equation f of x, y equal to 0. And that will give you a whole family of points where that holds. Typically will be a continuous curve, and that will be determined then by this equation f of x, y equal to 0. Now, the case we're interested in here for our current video is that we may have a situation like this, where we have f1 of xy equal to 0 and f2 of xy equal to 0. So we have two functions that have to satisfy this constraint, that they both have to vanish. And so then that will typically give you a solution, a specific solution that will be denoted here as xr, yr. So this is the root then. And geometrically what that is a situation where you have then the domain here being xy, and you have the two functions determining the two different curves where they vanish. So f1 of xy equal to 0 will give you this curve here, and f2 of xy equal to 0 will give you a different curve, and the point where both intersect is exactly that point that we're looking for, is the point that gives you the root xr, yr. Now, how do we proceed in this case? Let's establish some of the math, and then we'll go and find what the algorithm would look like. So suppose we're close to the roots somewhere in this neighborhood, and we're looking for a point, or rather we're standing at a point xy, and we want to find delta x, delta y, such that when we add that correction delta x and delta y to x and y, we land exactly on the root. So imagine that we're over here somewhere, and we're looking for exactly delta x and delta y that lands us exactly on the root. Suppose we're over here somewhere, there will be some delta x to the right here, and some delta y upwards, and that will land us exactly on the root. So can we find that delta x and delta y? That is what we're looking for. So if we have exactly that delta x and delta y, then we'll have solved the problem. And the conditions that determine the location of the root are these two, f1 xy equal to 0 and f2 of xy equal to 0. And so let's do a Taylor expansion then of f1 of x plus delta x and fy plus delta y around xy, around the point that we're taking as a reference, around their starting point xy. So then that will be equal to the function at xy, and then we have corrections coming from the first derivative of f1 with respect to x, and the first derivative with respect to y. So there's going to be changes in the x and y directions, delta x and delta y, that will affect the value of f1. And so there will be then first derivative of f1 with respect to x times delta x. That derivative is evaluated at our reference point xy. And then we have the derivative of f1 with respect to y, again evaluated at the reference point xy times delta y. So this is a typical two-dimensional Taylor expansion chopped off here at first order. There'll be higher order terms, so we're going to neglect those. We're going to assume that those are small. So if this is the expression for f1, then there's going to be an equivalent expression for f2, where you have, again, f2 of x plus delta x, y plus delta y, is going to be equal to the value of the function at the reference point xy, times plus two contributions coming from the fact that the function changes along the x-axis and along the y-axis. So there's going to be df2 dx times delta x and df2 dy times delta y. So now notice that we have these two equations, but we have four derivatives involved, f1 with respect to x and y, and then f2 with respect to x and y. It's important, that'll become important very soon. So we can rewrite this kind of messy two equations much more conveniently. And to do that, we will define some notation here. So we can rewrite this as a big vector f encoding the two functions f1 and f2 evaluated at the point x plus delta x, where we have encoded x vector as putting together the values of x and y into a vector, and then we have a delta x that also encodes delta x and delta y into this vector. And so when we add x plus delta x, we add component by component. And so this x plus delta x, of course, just encodes this x plus delta x and y plus delta y that are the arguments of the functions f1 and f2. On the right-hand side, we have f of x, which is encoding these two terms into one vector. And then we have this product of j and delta x. So I told you what delta x is, but what is this j? Well, the j is a matrix of derivatives that's called the Jacobian matrix. And it's written in this form. The first row is df1 dx, df1 dy, and the second row is df2 dx, df2 dy. So this then is what's going to determine our equations that determine our method. And you'll see why. So if our delta x lands us exactly on the root and we can neglect the higher order terms, then it must be that that little change will, when we implement it, will land exactly at the root of the function, and that is equal to 0. So that's by assumption. We're assuming that delta x lands on the root, and so that means that f of x plus delta x exactly vanishes. And this gives us an equation for delta x. So we know the value of the function at the reference point, we know the value of the derivatives at the reference point, but we don't know what delta x is. And so this equation determines delta x. And so the way that works is that we put this f on the other side of the equation. That gives us j times delta x is equal to minus f. And now we can put j on the other side of the equation if we use matrix inversion, and we then arrive at this equation where delta x is equal to minus j inverse applied to f of x. So remember, once again, this j is the matrix of derivatives evaluated at the reference point, the point where we started. Geometrically, that will be some point that's close to the root. We don't know exactly where the root is, but the point is somewhere in the neighborhood, assuming that we have some idea of what the function looks like. And then the same with the derivatives. We don't know the delta x, but we know the derivatives. And so we can calculate j, and we can calculate j inverse, or we can apply j inverse to that function evaluated at the reference point. We flip the sign, and then we obtain delta x. Now, in this process, we're neglecting higher order terms. So this delta x is only an approximation. And so this then gives us the Newton-Raphson method, where we pick a reference point x0, we calculate the right-hand side f of this equation, we calculate j, and then our job is to calculate delta x. This here is going to be the heavy part of the method. Here we're going to use a linear solver to calculate delta x by either solving this linear problem. This is a matrix vector equals to a vector, and so we can use a linear solver, or we can calculate j inverse directly in some cases, like in 2D or here, or in 3D. The inverse of the matrix calculated directly, and so then we can apply that inverse matrix to f. We flip the sign and we obtain delta x. So now that we have that delta x, what do? Well, we add it to x0. So that would be the correction that we need to arrive at the root. And that gives us an x1. But that x1 is only going to be approximate. And so what we do is we go back to the beginning, where wherever it says x0, we replace it with x1, with the new improved point that we calculated. And so now imagine that here it says x1, we calculate f of x1, j of x1, and we calculate the new correction that hopefully will be smaller, and that will take us closer to the true root. Now, this is basically the core of the algorithm, and the most difficult part is using a linear solver to find delta x. Most difficult, I mean computationally speaking. That, of course, is where the bulk of the time is going to be spent. But in 2D and 3D, that's not going to be too much time anyway. Things could get hairy and more complicated when you go into much higher dimensions. Now, when can things go wrong? Things go wrong if this inverse doesn't exist, or is approximately, or j is approximately singular. So that's when the determinant of j is 0 or approximately 0. And so in that case, this inversion of j, or this application of the inverse of j to f could go wrong. It will give you a delta x that is not small, or at least it's not small in some direction. And that would mean that it's not a small correction, and then the method could take you in some weird direction, and it may very well not converge. So you have to be mindful of that, and possibly attempt to evaluate the determinant of j before trying to do the inverse. That is easy to do in 2D and 3D. As you go to higher and higher dimensions, calculating the determinant, it's very expensive, and so you have to be mindful of that as well. So you see, as you ask to solve more and more complicated problems like this one here, with 2 equations and 2 unknowns, or 10 equations and 10 unknowns, then it could get more and more complicated and more demanding. But that's, of course, expected. Now, aside from that, and I basically implicitly already said it, this is generalizable to arbitrary dimension. So here, if you look carefully in this whole set of instructions, the only place where I maybe mentioned 2D is here, but this could have been 3D, 4D, 10D, it could be 100-dimensional vector, it doesn't really matter. So the method, once you establish this notation, the bulk of the method remains exactly the same, and what changes is the implementation. And that's about it. That's all I have for you today. I hope you enjoyed this video on finding roots in 2D and possibly in higher dimensions. And if you do enjoy this, consider liking and subscribing to the channel. And that's about it. I'll see you next time.